Sometimes we're interested in stating an opinion of the form probability of A given B, but we find it much easier to compute the probability of B given A. And those two things are not interchangeable. They're not the same probabilities. One of the most important theorems in conditional probability is Bayes' formula, which tells us how to convert one of those conditional probabilities into the other. So the idea is we would like to state opinions, probability of A given B, probability of A complement given B. This is 1 minus probability of A given B. But what's available, or easy to compute, is probability of B given A, or probability of B given A complement. Luckily, we can convert these into what we want. So the strategy for putting these together into the right formula is 1, first of all, recall that the probability of A given B, which is what we want, is the probability of A and B over probability of B. So we'll use that. Second, recall that the probability of B, which is there in the denominator, can be written as probability of A and B plus probability of A complement and B. So if here's A and there's B, here's the intersection A and B, and here outside of the A circle is A complement B. So if we put together the AB and the A complement B regions, together they make up B. And second, we recall that the probability of AB equals the probability of A times the probability of B given A by the multiplication formula. Now if we put all these together, this expression converts the denominator into a sum, and then each of the summands can be expressed as a product. And if we put all that together, let's see what we get. So together, these give us that the probability of A given B is probability of AB over probability of B, and the probability of AB is probability of A times probability of B given A, over probability of B is probability of AB plus probability of A complement B. And then we can rewrite each of these just like we rewrote the probability of AB there. So the numerator is the same, probability of A, probability of B given A. And then the denominator will convert this into also probability of A, probability of B given A. And that's going to be probability of A complement times probability of B given A complement. So what we have on the left-hand side is the conditional probability we want, probability of A given B. And we've expressed it completely in terms of the opposite conditional probabilities, B given A and B given not A. So if we're ever given those opposite conditional probabilities, the ones with the A and B in the wrong order from what we want, we can put them together into this fraction to make probability of A given B. And this formula is called Bayes' formula. All right, so let's do an example. We're going to do an example involving coins and urns containing marbles. So let's say that urn H contains one blue marble and one white marble. And urn T contains two blue and one white. Now let's say a fair coin is tossed. It'll either come up heads or tails, and we'll pick one marble out of whichever urn the coin tells us to pull a marble out of. So we picked one marble from the urn designated by the coin. The question is, if the marble is white, what's the probability it came from urn H? Or urn T? All right, well, we'll use this formula. Maybe I will erase everything that went into the formula and just leave the formula here. All right, so in this problem, let's let white be the event that we get a white ball and B be the event that we get a blue ball. So if we know what urn we're choosing from, it's easy to compute the probability of getting white and blue. So the probability of white, given that we're choosing from urn H, is 1/2. And that's also the probability of getting blue given that we choose from urn H. The probability that we get white given that we're choosing from urn T is 1/3, and the probability that we get blue given that we're choosing from urn T is 2/3. But the question says, if we select a white marble, what's the probability that it came from urn H? So we want the probability of H given W, or the probability of T given W. So we've got the conditional events in the opposite order from what we want, but that's okay, because we'll just use Bayes' formula and turn everything around. So the probability of H given W, the probability that the coin landed heads given that a white ball was chosen is, so H is going to be our A and W is going to be our B. So probability of H, probability of W given H over probability of H, probability of W given H, plus probability of H complement, which of course is T, probability of white given T. Okay, so now we've got this formula in terms of the conditional probabilities that were easy to compute given what we knew. So this is probability of heads is 1/2. Probability of white given heads is 1/2. And then on the bottom we have that product also, plus the probability of tails, which is 1/2. Probability of white given tails, which is 1/3. So that's 1/4 over 1/4 plus 1/6. Maybe I'll multiply numerator and denominator by 2 to make this 1/2 over 1/2 plus 1/3, which is 3/6 over 3/6 plus 2/6, 5/6. So 3/5. If we pull out a white ball, then the probability that it came from the H urn is 3/5. Also, the probability of tails, given that it's a white ball, must be 2/5. Because the probability of H complement given W equals 1 minus the probability of H given W. Let's maybe look at this in a Venn diagram if this last equality is not perfectly clear. So here's the event H in this circle, the event W in that circle. Here's H and W, and here's H complement and W. So the probability of H given W is number of elements in the set HW over number of elements in W, and the probability of H complement given W is number of elements in H complement W over number of elements in W. Or area over area, area over area if we're using continuous probability. This is for finite sample spaces. So that means that if we add these up, probability of H given W and probability of H complement given W, it should be the sum of these two fractions. But what's on top of the fraction? If we take all the elements in HW and all the elements in H complement W and put them together, we just get all the elements in W, which of course is 1. The end.